Hello, hi everyone. This is Rupesh. Today I'll be discussing phase transfer catalysis in Unit 2 of paper C205 green synthesis. Phase transfer catalysis. In many organic reactions, difficulties are encountered if organic compound is soluble in organic solvents and reagent is soluble in water. Then the two will react very slowly because the reaction takes place only at the interface. This problem can be overcome by using a catalyst which is soluble in water as well as organic solvent. Such a catalyst is known as phase transfer catalyst, which is abbreviated as PTC. Phase transfer catalysts are ionic in substance, generally quaternary onium salts, where the size of the hydrocarbon group in the cation is large enough to confirm good solubility of the salt in the organic solvent. In other words, the cation must be highly lipophilic, that is, it should be hydrophobic in nature. Coming to the reaction, whereas alkyl halides reacts with sodium cyanide in the presence of PTC gives alkyl cyanide plus a salt which is sodium halide. That is, this reaction can be carried out in the presence of PTC, whereas without PTC this reaction doesn't proceed, that is RCN, alkyl cyanide doesn't form. Why? Because this alkyl halide is soluble only in the organic solvent, whereas this is an ionic compound which is soluble in water but doesn't dissolve in organic solvent. Hence PTC is required to transfer the cyano group to the organic layer. Coming to this figure, as I said, you can see there is an interface here. This is an organic phase, that is organic solvent. This is an aqueous phase which has an water layer, and you can see there is a layer separating an aqueous phase and organic phase, which is called an interface. That is, without PTC, as I said, two will react very slowly because the reaction takes place only at the interface. Without PTC, only the reaction takes place at the interface. When PTC is added, then the sodium cyanide is transferred from the aqueous layer to the organic layer. Then that cyanide reacts with the alkyl halide, that is, halogen is displaced to form an alkyl cyanide. That is, the basic function of the PTC, phase transfer catalyst, is to transfer an anions from the aqueous phase into the organic phase. There are several factors. The following factors plays an important role in the successful use of PTC in a reaction. One such is an influence of solvent. Solvent must be immiscible with water and should also be an aprotic. For example, chloroform, benzene, tetrachlorocarbon, toluene, example, etc, etc, etc. And coming to influence of cation, the larger the number of carbon atom around the central nitrogen atom, the better is the lipophilicity of the catalyst. That is, around the nitrogen atom there should be a bulky group, then the lipophilicity of the catalyst is better. That is, hydrophobic compound should be around the central nitrogen atom. For example, coming to the example, tetra n-butyl ammonium chloride is a PTC, is the best example for a PTC. There is this formula is better than tetramethyl ammonium chloride. You can see butyl, n-butyl is a bulky group, that is 4n-butyl, tetra n-butyl is a bulky group compared to a simple methyl group. Coming to salt effect, addition of a alkali, that is NaOH and potassium carbonate increases the extraction coefficient many times and thus increases the rate of a reaction. Coming to the mechanism of phase transfer catalysis, the mechanism is better understood from the following example, that is heating and stirring a mixture of 1-chloroethane for several days with sodium cyanide gave particularly no yield of 1-cyanooctane. That is heating a mixture of 1-chlorooctane, the presence of sodium cyanide yields no 1-cyanooctane. That is 1-cyanooctane is expected but we didn't get any product. Whereas if you add a small amount of PTC, then the product is formed in just about 2 hours in the presence of a PTC, which is tetra-N-butyl ammonium chloride. As I said, PTC is an quaternary ammonium salt. This is an ammonium salt. There are several ammonium salt. One such is an ammonium salt, ammonium chloride salt. This reaction doesn't take place without the catalyst. Since the cyanide ion cannot cross the interface between the two phases, that is organic phase and aqueous phase, the reaction is that sodium ions are solvated by water and solvation energy couldn't be present in any media or in any organic phase. Thus, cyanide ion cannot cross the barrier or interface without the sodium. So sodium is very important here. Since that would destroy the electrical neutrality of each phase. In contrast to sodium ion, the Q plus, which is a PTC, the positive cation which is present in the PTC, which bears sufficiently a large alkyl groups, that is a bulky groups mainly solvated in water and prefers organic solvents. If a small quantity of such a salt is added, that is if a small quantity of PTC is added, 3 equilibria are set up. Then these equilibria are represented in the figure. This is the equations. You can see there is a 3 equilibria which is set up in the equation. You can see this is a equation which happens in the aqueous phase, and this is the equation happens in the organic phase. First of all, this is an PTC. It may be ammonium or phosphonium or whatever, quaternary ammonium salt. Here quaternary ammonium chloride reacts the sodium cyanide to form an cyanide group. That is, a PTC is carrying the cyanide ion to the organic phase. You can see that the cyanide ion from the aqueous phase is carried to the organic phase, and this cyanide ion reacts with the alkyl halide. Here it is alkyl chloride. It is to form an alkyl cyanide with the formation of an quaternary ammonium chloride, which is recovered in the final stage. That is, you can see from the chloride ion, from the cyanide ion in the aqueous phase, it is transferred to the organic phase, which reacts with the alkyl chloride to form an alkyl cyanide. At the beginning of the reaction, the key anion present in the aqueous phase is cyanide ion. This gets carried into the organic phase. That is, this cyanide ion from the aqueous phase, it is carried into the organic phase where it reacts with alkyl halide to produce RCN and chloride ion. Then this chloride then gets carried into the aqueous phase, and that is in equation 2 and 3 entirely takes place in aqueous phase. This allows quaternary cyanide to be regenerated. Types of phase transfer catalyst and reactions. PTCs are quaternary ammonium salt, as I said before, such as ammonium, phosphonium, antimonium, and arsonium salts. However, in practice, only the limited number of ammonium and phosphonium salts are used. There are many commercially available PTCs, that is phase transfer catalyst. One such is tetra n-butyl ammonium chloride, tetra n-pentyl ammonium halide. Here halide may be chloride, bromide, or iodide. Here tetrahexyl ammonium halide. This is trimethyl benzyl trimethyl ammonium halide. Here benzyl triethyl ammonium halide, benzyl tributyl ammonium halide. Here trihexyl propyl ammonium halide. Here benzyl triphenyl phosphine ammonium iodide. This is a phosphonium salt. Quaternary phosphonium salts are more expensive than the quaternary ammonium salts, but they are more thermally stable than the corresponding ammonium salts. Coming to the reactions, that is phase transfer catalyzed reactions. Liquid phase transfer catalyzed reactions. Originally, the PTC, the phase transfer catalyzed reaction, was performed using an aqueous phase and an organic phase. That is, both are liquids here. This technique is called as a liquid phase transfer catalyzed reaction. Coming to the second one, solid liquid phase transfer catalyzed reaction. Water sensitive reagent can't be used in the above method. That is, water sensitive reagent can't be used in the liquid phase transfer catalyzed reaction. In such cases, solid ionic reagent is used, which is suspended in an anhydrous organic solution of the substrate. This is very important. It should be an anhydrous organic solution of the substrate. The PTC catalyst transfers the anion from the surface of the crystal lattice, that is, from the surface of the solid ion to the organic phase. For example, generation of a dichlorocarbene by using a sodium salt of a trichloroacetate suspended in an anhydrous chloroform in the presence of catalytic amount of quaternary salt, that is a PTC. You can see this is a trichlorosodium acetate. This, in the presence of PTC in chloroform, this dichlorocarbene is generated. Whereas without PTC, you cannot generate a dichlorocarbene. Whereas you can see this is a solid and this is a liquid here. Whereas PTC, you can see this is a best example for solid liquid PTC phase transfer catalyzed reaction. This is a carbene here. This is not a CH2, it's just a C with a 2 pairs of electrons, which is a electron deficient molecule. However, if water is used in this reaction, sodium trichloroacetate is decomposed as here, that is sodium trichloroacetate in the presence of water, they get decomposed to sodium bicarbonate plus chloroform. Coming to the next one, solid gas phase transfer catalyzed reaction, where two phases like solid and gases are involved. The gaseous phase is continuously passed through a fixed bed of a solution salt, fixed bed of a reaction salt and thermally stable PTC. Generally, these PTCs are observed on a silica gel. Silica gel is nothing but a crystalline silicon oxide, which is SiO2. This technique is used in simple nucleophilic displacement such as synthesis of halides, alcohols and alkyl esters. There is a general reaction for the displacement reaction. That is, you can see alkyl halide reacts with an nucleophile. In the presence of a PTC, you get an corresponding alkyl halides or alkyl esters or alcohols. That is, you can see an alkyl halide is converted to an corresponding alkyl esters if Y is carboxylate ion. Coming to the next one, tri-phased catalyst. The name itself indicates there is a 3 phases, which is an organic phase, aqueous and solid catalyst are present. The solid catalyst is generally a polymer supported and is insoluble in water or organic solvent. The tri-phased catalysts are divided into different categories based on the nature of active sites. Insoluble ammonium and phosphonium salts, which are cross-linked to polystyrene resin. Such catalysts are insoluble in medium. These are the tri-phased catalyst, which is a best example of a tri-phased catalyst. And you can see an polymer which is a repeating unit here, and even you can see a repeating unit here. Advantages. Phase transfer catalyzed reactions have considerable advantages over the conventional procedure. That is, they doesn't require vigorous conditions, that is heating up to 200-300 degrees. That doesn't require any vigorous conditions, and the reactions are very faster. They doesn't require expensive abiotic solvents. They doesn't require any high temperature and pressure. The reaction usually occur at low temperature. There is no need for anhydrous conditions since water is used as one of the phases. With the help of PTC, the anion is available in organic solvent, therefore its nucleophilicity increases. Many reactions which require strong bases like alkoxides, sodamide, sodium hydride, that is NaH, etc., can proceed by hydroxide ion. Since hydroxide ion becomes strongly nucleophilic in presence of PTC, almost all reactions can be carried out except which are those sensitive to water. Preparation of catalyst, that is preparation of PTCs. Preparation of quaternary ammonium, phosphonium and arsonium salts, that is common methods by simple alkylation of a tertiary amines, phosphines and arsines. Coming to the first one, trialkyl ammonia reacts with alkyl halide to get the tetraalkyl ammonium halide. Here halides may be bromide or iodides. Coming to the next one, the synthesis of an phosphonium and arsonium PTCs, that is triphenyl phosphine or arsine, that is equimolar volume of an phosphine or arsine reacts with the appropriate halides. This is an alkyl halides. Just warming, just heating to 50 to 100 degrees Celsius, we get an corresponding phosphonium salts or arsonium salts. Yeah, that is equal mixture of this phosphine or arsine and the appropriate. This may be a alkyl bromide or iodide is just warm for several hours to 2 to 3 days. That is, this reaction is carried out for several days in ethanol or acetonitrile as solvents. Recrystallization of this phosphonium or arsonium salt PTCs can be done using ethanol or using ethanol ether mixture or using ethyl acetate for lower salts. The active PTC can be prepared by exchanging their anions as the quaternary salts. This is normally achieved by shaking a solution of a quaternary salt in DCM, that is methylene chloride or dichloromethane, with an excess of aqueous solution of NaCl. That is, this tetraalkyl ammonium bromide reacts with NaCl. This is a PTC reacts with NaCl, it gets converted to an chloride. That is, bromide form of PTC is converted to an chloride form of PTC. This is also called as exchange of halides or reaction of halide exchange. Coming to the examples, that is, tri-N-hexyl ammonia reacts with N-hexyl bromide under reflux conditions. In methanol, we get an tetrahexyl ammonium bromide. This is a general example for the preparation of PTC, but not the example for this equation. The solvent is removed, that is methanol is removed under reduced pressure. Isopropyl ether is added to the mixture and filtered at lower temperature to remove if any water is there, and crystallized using ethyl acetoacetate. Finally, the compound is washed with petroleum ether to remove any non-polar impurities. Coming to the second example, that is this is an N-hexyl ammonium bromide reacts with this dimethoxy sulfone in the presence of a chlorobenzene, which is a solvent here. This is reflux at 100 degrees Celsius for 45 hours to get the corresponding PTC with the formation of an methyl bromide. This, in the presence of a strong acid in dioxane solvent, we get the corresponding tetra N-hexyl ammonium hydrogen sulfate PTC with the formation of a methanol. Here this methyl bromide is removed by distillation and this chlorobenzene solvent is removed by steam distillation. After simple workup, the product is recrystallized using ethyl acetate. Advantages of PTC. PTC is used in several reactions. One such is substitution reaction. First example is a synthesis of alkyl fluorides from alkyl halides. This is a general equation for the synthesis of alkyl fluorides. Alkyl halide, to be in general, that is X is equal to chloride or bromide. Alkyl fluoride or alkyl bromide reacts with potassium fluoride. In the presence of PTC, we get an corresponding alkyl fluoride. That is, PTC helps in transferring the fluoride ion from the aqueous phase to the organic phase. That fluoride ion gets attacked here with the elimination of chloride ion to form a corresponding alkyl fluoride. This is also an example for an exchange of halides or else halide exchange reactions. Alkyl fluorides or bromides reacts with, that is, as I said, alkyl fluorides or bromides reacts with KF in the presence of PTC to give alkyl fluoride. This procedure is far superior to the conventional methods that requires anhydrous KF and high boiling polar solvents. That is, this shows that the conventional method is used under highly reflux conditions, that is used under high temperature, whereas this reaction is carried out at normal room temperature. Coming to the next synthesis of alcohols from alkyl halides. The displacement of halogen by hydroxyl group in presence of a simple PTC is very difficult. This is because the hydroxide ion is highly hydrated compared to halide. Therefore, it tends to be purely transferred into the organic phase. In addition, the quaternary ammonium hydroxide are thermally unstable. Once the alcohol is formed, it readily converted into alkoxide, resulting in the formation of an ether. So the concentration of hydroxide ion in the aqueous phase should be high enough to maintain the high proportion of a catalyst in the form of an Q plus OH minus form, that is PTC in the hydroxide form. This is the best example, that is PTC in the chloride form gets converted to the PTC in the hydroxide form. That is PTC in the chloride form reacts with the hydroxide ion to form an PTC in the hydroxide form. The displacement of an halogen by hydroxide ion is carried, which is difficult, is carried by using a betaine quaternary salt. This is a betaine quaternary salt, which is a derivative of a glycine, which is also called as trialkyl ammonium acetate. This shows, that is this betaine quaternary salt shows 10 to 50 fold, that is 10 to 50 times greater activity than normal tetraalkyl ammonium salts. Coming to the mechanism, whereas this betaine quaternary salt reacts with alkyl bromide to get an corresponding alcohol. That is, this is the structure of an betaine quaternary salt. This negative charge forms a double bond here, whereas this attacks the alkyl group, the elimination of bromide, and this will be in the salt form. Then this reacts with the hydroxide group, that is sodium hydroxide or potassium hydroxide, and there will be exchange of an anion to form a corresponding quaternary. This is a PTC with the bromide form, whereas this is PTC with the hydroxide form, and this hydroxide attacks the alkyl group with the formation of an corresponding alcohol, and the betaine quaternary salt is recovered. The greater activity is due to active rapid carboxylate displacement followed by an anion exchange and hydrolysis here. Coming to the example, that is alkyl halide reacts with sodium cyanide in presence of PTC. You get an alkyl cyanide, which is the best example. Coming to the second one, phenyl ethyl chloride reacts with sodium bromide in the presence of a PTC, which is benzyl trimethyl ammonium chloride, to the corresponding phenyl methyl bromide. Coming to the next example, you can see benzoyl chloride reacts with sodium cyanide in the presence of an PTC, which is tetra N-butyl ammonium chloride. We get the corresponding benzoyl cyanide. Whereas without PTC, we get an adduct, which is a formation of an ester here. Coming to the next one, synthesis of azides from aryl or alkyl halides. This is an pyrrolizole derived halide, reacts with the sodium azide in the presence of this PTC. This is an tetra N-butyl ammonium hydrogen sulfate. In DMSO solvent, this is a highly polar solvent. Just warming the reaction at about 45 to 50 degree. In 1 hour, we get the corresponding acid. Even alkyl nitrites, alkyl cyanates and alkyl thiocyanates and paratoluene sulfonates using the equation given below can be synthesized using equation. That is, alkyl bromide reacts with the sodium nitrate, and this is the cyanate, this is the thiocyanate, this is the paratoluene sulfonate to the corresponding alkyl halides. Alkyl nitrates or cyanates, you can prepare the corresponding alkyl nitrates from the corresponding sodium nitrate. Elimination reactions. The next synthesis is elimination reaction. Alkyl halides reacts with aqueous NaOH in the presence of PTC to give alkenes. This is an alkyl halide, reacts with aqueous alkali in the presence of a PTC, that is N-tetrabutyl ammonium hydrogen sulfate. That is, this PTC transfers this hydroxide group to the organic phase, whereas after transferring, the OH minus abstracts this proton, and this forms a double bond here with the elimination of a bromide ion to form the corresponding alkene. Advantages of this reaction is, which is a convenient here, earlier dehydrohalogenation, that is, this is a dehydrohalogenation step, was carried out with alcoholic KOH or soda amide or liquid ammonia. Here, just using a simple PTC, you can convert the alkyl halides to the corresponding alkenes, which is a dehydrohalogenation reaction. Coming to the next one, addition reactions. Under this, addition of dihalocarbons to organic molecules. Dihalocarbons are synthetically useful intermediate. They are normally generated by the action of base on chloroform. That is, there is a hydroxide ion from the alkali, that is NaOH. This hydroxide abstracts a proton to form the corresponding anion. This on losing an halide to form the corresponding carbene, which is a electron deficient molecule. These reactions usually require anhydrous condition. Since dihalocarbene, this may undergo hydrolysis in the aqueous solution. Coming to the examples, where cyclohexene reacts with chloroform and NaOH to form the corresponding compound. That is, here chloroform reacts with NaOH to form this carbene, and this carbene, the carbene so generated, reacts with this cyclohexene to form the corresponding compound in the presence of PTC. Without PTC, you just get the 5% of this compound, whereas in the PTC, that is benzyl triethyl ammonium chloride, you get the 70% yield, whereas without PTC, you just get the 5% yield. Coming to the second one, which is similar as the first one, that is a styrene, which is an conjugated aromatic ring, reacts with the carbene so generated using this chloroform and NaOH, but the reaction is slightly heated at around 40 degrees Celsius. The reaction is carried out for 4 hours. Since it is an aromatic and sp2 hybridized carbons, in the presence of this catalyst, you get the corresponding dihalo compound. That is, a dihalocarbene generated in situ by PTC method has been used for the several number of synthetic purposes. That is, PTC is used to form in many reactions. One such is additions to imines. This is an imine reacts with the dihalocarbene generated using chloroform plus NaOH to form the corresponding dihalo. This is an geminal dihalo compound in the presence of this catalyst. And coming to the second one, insertion into CH bond, that is carbene is inserted in this position to form the corresponding compound, that is this is a THF to the corresponding substituted THF. Coming to the reactions with alcohols, where using carbenes so generated using chloroform and NaOH, alcohol is converted to an corresponding alkyl halide in the presence of this catalyst, that is benzyl triethyl ammonium chloride, and this reaction goes through the intermediate mechanism, goes through this intermediate, that is, as I said, dihalocarbene is a electron deficient, therefore the lone pairs on oxygen attacks the dihalocarbene to form this compound, and the lone pairs on chloride attacks the alkyl group with the formation of a CO double bond O, and this takes up a proton to form the alkyl halide plus HCOCl, that is formal chloride, which is highly unstable. Coming to the next one, reaction with amines. Amines can be converted to the corresponding isonitrile, or else it is also called as isonitrile. This moiety is called isonitrile or isocyanide. This alkyl amine is converted to an alkyl isocyanide or alkyl isonitrile. In the using dihalocarbene, so generated using chloroform and NaOH, and this reaction goes through this mechanism, that is, there is a nucleophilic attacks the carbene to form this compound, this on losing a proton, and the correspond this is a dehydrohalogenation reaction, that is HCl is eliminated to form the corresponding imine, and again one more molecule of HCl is liberated to form the corresponding isonitride. Coming to the next next advantages, that is oxidation reaction, that is PTC is used in the oxidation reactions. One such oxidation is permanganate oxidation. It is a derivative of heptavalent manganese, which is a very powerful oxidizing agent. Its reactivity depends to a greater extent whether it is used under acidic, basic or neutral conditions. It is generally used as an aqueous solution. Oxidation using solution of KMnO4 can be affected in presence of PTC. Permanganate ion strongly associates with quaternary cation and readily extracted into the organic phase by PTC. And this is an quaternary cation, that is a PTC with a positive charge. Strongly associates with the permanganate ion. This is a PTC with the permanganate form. It reacts much faster in organic phase. It oxidizes, that is this PTC with permanganate form oxidizes olefins, alcohols, nitriles and the alkyl and aromatic chains. Organic phase oxidants like purple benzene, triphenyl methyl or sodium permanganate could be readily prepared and used as an organic phase oxidants. A solution of potassium permanganate in benzene is stirred with a catalytic amount of PTC, and the benzene layer can be used as an organic phase. As you can see, this is an octene reacts with KMnO4 in the presence of a PTC to form the corresponding vicinal diol. That is the yield we can get up to 50%, whereas without PTC we just get the 5% of this diol. That is, this PTC transfers this permanganate ion to the organic phase. That transferred permanganate ion oxidizes the alkene, oxidizes the olefin to the corresponding diol. Under the oxidation reaction, the next compound is an chromate oxidation, that is chromic acid, a derivative of a chromium, is one of the most versatile oxidizing agent. Chromic acid oxidation is a useful process in organic synthesis. In general, PTC added chromate oxidizing agent are milder but have high selectivity. A commercial resin which is called amberlite A26 can be converted into the chromate ion form by stirring the chloride form of the resin. That is, meaning this amberlite A26 is generally in the form of an chloride ion form. This is stirred with the chromate ion which gets converted to the chromate form. That is, amberlite A26 chloride form in the chloride form is converted to the amberlite A26 in the chromate ion form. The resin so obtained, that is The resin amberlite A26 chromate ion form so obtained is stable at room temperature and used for the oxidation of alcohols, allylic halides in various refluxing solvents to give the corresponding aldehydes or ketones in very good yields. In general, conventional method yields the carboxylic acid as the products. This is the general example, that is alcohol reacts with the PTC to get the corresponding carboxylic acid, that is amberlite A26 in the chloride ion form reacts with the chromic acid, then it is converted to the amberlite in the chromate ion form, which is in the organic phase now, which oxidizes the alcohol to the corresponding carboxylic acid. Next one such oxidation is hypochlorite oxidation. Hypochlorite anion can be transferred into the organic solution by an Q plus ion, that is a PTC quaternary cation, and used to prepare the aldehydes from benzylic alcohols, carboxylic acid from aliphatic alcohols, ketones from secondary alcohols, and nitriles from primary amines in good yields. That is, as I said, this is an alcohol which gets converted to the this is an benzyl alcohol converted to the benzaldehyde in the presence of an hypochlorite, that is sodium hypochlorite, in DCM in the presence of an PTC, which is a tetra N-butyl ammonium halide. The reaction is generally carried out for 75 minutes. You get the corresponding aldehyde in good yields. The same reaction is that that is the next one is the octanol reacts with the same, that is sodium hypochlorite in DCM. In PTC you get the corresponding ketone. Third one, which is a general one, that is alcohol is converted to the aldehyde in the first step using the excess amount of PTC and hypochlorite. It gets converted to the corresponding carboxylic acid. Coming to the fourth example, you can see the amine, alkyl amine is converted to the corresponding nitrile, which is an oxidation reaction, whereas the reverse is the reduction reaction which we studied in the previous classes, that is nitrile can be converted to amine using reducing agents such as LAH, whereas here we are studying oxidation of amines to get an corresponding nitrile. Reduction reactions using PTC. Hydrate reduction, that is, this is a tetraalkyl ammonium borohydrate. Tetraalkyl ammonium borohydrate have been used as a reducing agents in this system having special solubility problems. Tetraalkyl ammonium borohydrate are generally obtained in situ by the action of tetraalkyl ammonium halides with sodium borohydrate. These salts transfers the borohydrate anion from an aqueous phase to the organic phase. The reduction rate is increased, but it is inconvenient for preparatory purposes. That is, the reduction is very good, the yield is very good, but the preparation of an PTC, that is tetraalkyl ammonium borohydrate, is very difficult. In general, the compound is reduced in organic solvent with sodium borohydrate, water and appropriate PTC for 1 to 7 hours. These are the quaternary ammonium salts used for the reduction. This is one of the best catalyst, best PTC used for the reduction of an aldehyde and ketone to the corresponding alcohol or carboxylic acid, corresponding alcohols. For example, that is aldehyde is converted to the corresponding alcohol in the presence of a PTC and sodium borohydride. That is, borohydride in the presence of PTC gets transferred to the organic phase and then reduces the aldehydes to the corresponding alcohols. This is all about phase transfer catalysis. In the coming classes, I will discuss about ground ethers. Thank you very much.